The eagle has landed. RWKV is a 7 billion RNN that outperforms all transformer in its weight class without even paying attention. Earlier this week, like at the end of January, RWKV 5 V5 Eagle touched down, making waves as one of the first non-attention based architectures to surpass transformer level of performance. So what is it and what's it all about? We'll dive deep into this in this video. So notice that it's a non-attention based architecture. We have a blog from May 15, 2023 that came out on the Hugging Face blog. So ChatGPT and chat-powered application have captured significant attention in the natural language processing domain. The community is constantly seeking strong, reliable, and open source model for the applications and use cases. We've seen lots of models making a way into this world. The community is constantly seeking strong. The rise of these powerful models stems from the democratization and widespread adoption of transformer-based models, first introduced by Vaswani et al. In 2017. So we know about the Attention is All You Need papers, which was introduced in 2017, which propelled all of this widespread, which propelled a pathway for the development of transformer-based models, and which ultimately aided in this widespread adoption of this large language models and AI systems. First, the Vaswani et al. The research that introduced transformers, and those were encoder and decoder based. Encoder based models gave us natural language understanding tasks like text classification, entity recognition tasks. Those were just encoder based, and the decoder based are also called autocausal transform models, which are good for the next word prediction and for text generation. So throughout this blog post, we will introduce the integration of the new architecture RWKV that combines the advantages of both RNNs and transformers that has been recently also integrated in the Hugging Face library. Before transformers, the most advanced model for sequence to sequence and text based tasks were RNN and LSTM based models. With the introduction of the transformers architecture and the attention, self-attention, and multi-head attentions, then the sequence classification, the sequence tasks were greatly enhanced because of the parallelization process and how they were able to use the attention mechanisms. So the RWKV project was kicked off and is being led by Bo Peng, and he has also various other artifacts that he is constantly enhancing, like the RWKV.cpp, quantization, scalability, as in data processing and scraping, research, chat fine-tuning, multimodal fine-tuning. The GPUs for training RWKV models are donated by Stability AI. So if we look at the transformer works, I just mentioned about this. So in RNNs, it takes the input current token, the previous state, and computes and predicts the next token and the predicted next state. So every state is updated along with the sequence of text that comes in. However, if you see, because RNNs use the same ways to compute predictions at every step, they struggle to memorize information for long-range sequences due to the vanishing gradient issue. The major problem with RNNs, one of the major problems was the vanishing gradient issue. That means the gradient, if spread over a long time, had changes that were becoming to start to become insignificant. I mean, over the long run, the gradients changes would be so minimal that it was vanished. What I mean here is, in a neural network training process, there is a forward pass and a backward pass. So in the backward pass, the gradient are updated along with the loss function. So the vanishing gradient is, after we went to the first pass, the forward propagation, and changing its loss, when you had to come back for as the back propagation, the over long sequences, the gradient changes that needed to be done was starting to get reduced so much that it were in the values close to 0. That means no values were being graded at the end of the training period. In the transformer architecture, the input tokens are processed simultaneously in the self-attention module. The tokens are first linearly projected into a different spaces using the query, key, and value weights. The resulting matrices are directly used to compute the attention score through softmax as shown below, then multiplied by the hidden states to obtain the final hidden values. This design enables the architecture to effectively mitigate the long-range sequence issue and also perform fast inference and training compared to RNN models. To understand the query, key, and value, and the attention, the self-head attention mechanism or the multi-head attention mechanism, you can follow Jay Alamar's blog post. It's a really good blog post that understands, that helps us understand it's called the illustrated transformer, and if you look at it, it's a very good learning tool that will help you understand how the transformer architectures work. And we will also further delve into it deeper in our next video. But for now, let's talk more about the RWKV architecture. It's inspired by Apple's attention tree transformer. So there has been previous works on trying to work around methods that did not have attention much. The architecture has been carefully simplified and optimized such that it can be transformed into an RNN. In addition to a number of tricks that has been addressed, such as token shift and small init embed. So token shift and small init embed are some of the additions to this model. Like, the technical details are not out yet, but these are some of the things that has been added into this RWKV architecture to boost the performance and to match GPT level performance. Without these, the model wouldn't be as performant. So the details are yet to be out fully, but it will be out. So for their training, there is an infrastructure to scale the training up to 14 billion parameters. As of now, some issues have been iteratively fixed. So we can also say that RWKV as a combination of RNNs and transformers. How to combine the best of transformers and RNNs? The main drawback of the transformer based models. So let's look at the main, because transformer based models help us understand language better, and it has propelled the development of this AI revolution. But there are also drawbacks associated with it, and people are trying to come up with solutions like the Mamba and the Hyena models. So but one of them is let's look at the drawback. The main drawback of transformer based models is that it can become challenging to run a model with a context window that is larger than a certain value, as the attention scores are computed simultaneously for the entire sequence, because it expands quadratically. RNNs natively support very long context lengths, only limited by the context length seen in training. But this can be extended to millions of tokens with careful coding. So the major drawbacks of traditional RNN models and how RWKV is different. Traditional RNN models are unable to utilize very long contexts. LSTM can only manage 100 tokens, because we talked about the vanishing gradient issue. However, RWKV can utilize thousands of tokens and beyond, as shown below. This figure shows the LM with loss respect to different context lengths and model sizes. And also other thing, the traditional RNN models cannot be parallelized when training. RWKV is similar to linearize GPT, and it trains faster than GPT. So these issues were solved by transformers, but still by combining the advantages into a single architecture, their hope is that I can grow into RWKV can grow into become more than the sum of its part. If we look at the attention formulation for RWKV, the model architecture is very similar to classic transformer based models. That is an embedding. It has an embedding layer, this text embedding layer, which converts the text tokens into embeddings, multiple identical layers, layer normalization, and a causal language modeling head to predict the next token, like the decoder based models. The only difference is on the attention layer, which is completely different from the transformer based models. So it's almost similar to transformer based models, but it does not have attention. It's the attention based is completely different. Instead of the key value query pair, it combines RWKV to gain so there are some existing checkpoints, and they're coming with the instruction fine-tune. The details are not out yet, and when it comes out, I'll be coming out with a video to explain that too. Bo has also trained a chat version of the RWKV architecture, the RWKV4 Raven model. It is RWKV4 pilot trained on the Alpaca, Code Alpaca, Guanco, GPT-4 all, and more data sets. If you wanna test it out, it has an Hugging Face integration, so you can easily check it out and experiment with it. I've done that, but so I just got disconnected. So if I will just run this, and we will see it in a while. So before that, yeah, so you can go and check out the Illustrated Transformer by J. Alama, and it'll help us understand transformer models more. So RNNs, classically the neural networks use sequence. We talked about it. We talked about how transformers, sequential natures of RNNs, they are hard to massively parallelize. So that was a blog that came out in May of 2023. Then another blog came out in March of 2023. Before the Hugging Face blog, and it describes, if you want to go into the technical post, it's here, and in the technical post, what's there are how the model works, text generation, like goes into the depth details of the blocks, like embedding vectors and tokenization, all that stuff. If you have some time, you can check it out, and if you're really interested, you can check it out in this blog there. But let's move on and see that a transformer processes all tokens at the same time, comparing each token to all previous tokens simultaneously in parallel. Specifically, the attention calculates key value and query vectors for each token. The contributions between all pairs of tokens are computed using those. In addition to being able to speed up training process through massive parallelization, large transformers generally score better than RNN on benchmarks. Yeah, so in addition to being able to speed up training through massive parallelization, large transformers generally score better than RNNs on benchmark. That's true. And so what we can see the major thing. So we basically have a model that trains like a transformer, except that for long context length is not expensive. What I'm trying to say is like it is we use the training transformer type formulation of the architecture, which allows massive parallelization with a sort of attention with linearly with the number of tokens. For inference, we use an equivalent formulation which works like an RNN with a state. Okay, but what about the performance? Since RWKV and RNN it is natural to think that it can't perform as well as a transformer on benchmarks. Also, this sounds like linear attention. None of the many previous linear time attention transform architectures like linformer seem to take off. And let's talk about the cost. And this one just came out January 8. That was the pre-research that led to this one, the RWKV, and now RWKV equals 7B. Soaring past transformers with 1 trillion tokens across 100 plus languages. 100 plus languages, can you believe that? Okay, is built on a the Eagle 7B in short, let's go through it. Eagle 7 billion parameter is the parameter, the number of parameters is the number of size that the model utilizes to understand the language in context. So it's built on the RWKV V5 architecture, a linear transform with 10 to 100x plus lower inference cost. It now ranks as the world's greenest 7B model. It's trained on 1.1 trillion token across 100 plus languages. It outperforms all 7 billion class models in multilingual benchmarks. It approaches Falcon 1.5 trillion, Llama 2 trillion, Mistral greater than 2 trillion level of performance in English evals. It trade blows with MPT-7B, all while being an attention-free transformer. It is a foundation model with a very small instruct fine-tune. Further fine-tuning is required for various use cases. Okay, so these are some of the performance details by using RWKV along with other models that are in the market like Mistral, Llama, Falcon, MPT, OpenLlama. These are all open source models, and it performs in part and even succeeds, like it performs better than most of the language other open source models in that same weight category. So this is enormous. Like, you mean, like this performs great, and that's so awesome. Yeah. So in detail, in summary, you could go through it, and perhaps a good dataset plus scalable architecture is all you need. English performance details. So let's look at the English performance. So once again, we see a huge overall jump from RWKV V4 to V5 architecture. And this section says perhaps a good dataset plus scalable architecture is all you need. A notable observation was that our checkpoints near the 300 billion token points show similar performance to Pythia. And this is consistent with previous spiral-based experiments on RWKV V4 architecture that linear transforms like RWKV scales. Built-in inclusive AI for English in this world, not just the English. So this is a multi-language model, and it has its multi-language model future plans. This release marks the release of the strongest linear transformer to date. While it may not have succeeded in passing Llama 2 and Mistral, it provides strong evidence of the following. The RWKV V5 model architecture scales similarly to transformers with a similar token count. You can achieve a near Llama 2-like level of performance with a substantially lower inference cost. While supporting multilingual level of performance, we plan to follow by pushing ahead with acknowledgement. And so this is the Hugging Face hub that you can look at and get the try it out for yourself. I've done that. I've done with the 1 billion model this time, but we can do it again with 7 billion models in the next video. And the great yet too. So I will come up with an experimentation working with this one in the next video. So thank you everyone, and enjoy your evening.